To get an appropriate understanding of the current state of the Martian atmosphere, it is necessary to describe the hypothesized history of Mars as a planet. The time from the formation of the solar system around 4.5 billion years ago can be divided into three traditional periods used in the Mars geologic calendar: the Nochian, Hesperian, and Amazonian periods. The exact boundaries of these periods are hotly debated. The ages are determined primarily from crater counts and correlating, but there are lots of assumptions that go into translating the crater record into absolute ages. The Nochian period, from 4.5 to 3.5 billion years ago, is characterized by high rates of impacts from meteorites and asteroids, and also by extreme volcanic activity bringing forth large amounts of carbon dioxide and water vapor into the atmosphere. These gases were able to trap heat and likely allow for liquid water to flow on the surface. Today we see extensive evidence of large lakes and oceans that may have existed during this period. The Hesperian period, from 3.5 to around 3 billion years ago, is a transitionary period where Mars lost the majority of its atmosphere and became the cold, arid planet we observe today. Vast oceans froze and sublimed into the atmosphere. As the sun became brighter, solar winds and radiation stripped most of the atmosphere away from the planet's gravitational field and was lost to space. The Amazonian period dates from roughly 3 billion years ago to present, and can be described as the stagnant period of Mars where its appearance has remained unchanged. These hyper-arid conditions have persisted with only seasonal or obliquity-driven variations in geologic and atmospheric cycles. The current state of the Martian atmosphere is drastically different from that on Earth and early Mars. The gaseous species consist of 96% carbon dioxide, 2% argon, 2% nitrogen, 0.15% oxygen, 0.05% carbon monoxide. The pressure averages around 6 millibar or 0.6% of Earth's pressure. Such a low pressure is well below the triple point of water, only allowing water to exist as ice or vapor depending on the temperature. The lack of appreciable atmosphere prevents any homogenizing heat transfer by convection, so the temperature at the surface of Mars varies greatly depending on the amount of direct exposure to solar radiation. Surface temperatures vary from about negative 145 degrees Celsius to as high as 35 degrees Celsius. These extremes can be reached in cycles of varying planetary obliquity or tilt, as the solar radiation is unevenly distributed across the Martian surface. The current atmosphere can be divided into 4 layers: the exosphere, the thermosphere, the middle atmosphere, and the lower atmosphere. It is important to note that the scale height of Mars's atmosphere is 3 kilometers higher than Earth's due to the lesser gravity, allowing particles to exist farther away from the surface. The carbon dioxide cycle is particularly important to understand, as it makes up practically all of Mars's atmosphere. As carbon dioxide in the atmosphere is shaded seasonally during winter at one of the poles, the temperature drops low enough, allowing for CO2 condensation, forming large, dry ice polar caps. When sunlight is again introduced, the ice sublimates directly into gaseous carbon dioxide. The CO2 likely formed a thick layer of atmosphere around early Nochian-era Mars with temperatures high enough to limit this condensation. A particular conundrum scientists faced was describing the extreme loss of CO2 over time to present concentrations. Research hypothesized precipitation of carbon dioxide to carbonate, which was then stored in the lithosphere. Once rock samples were analyzed for carbonate compounds, this theory only accounted for a fraction of the total loss of atmospheric carbon dioxide. A new hypothesis described the loss of carbon to space via photodissociation. Photolysis of CO2 produced carbon monoxide and oxygen, which then could photolyze again to form oxygen and carbon. The abundant isotopes of carbon, carbon-12 and 13, provided the final clue to confirm this theory. The Mars Science Laboratory on the Curiosity rover analyzed the ratio of carbon-12 to 13 in rock samples and found carbon-13 was much more abundant. As carbon-12 has a lighter nucleus, the kinetic energy from the high-energy photons and bond dissociation imparted on the lighter isotope more easily accelerated the lighter carbon to escape velocities. This process of solar stripping has been analyzed by the MAVEN spacecraft, which entered Mars's orbit in 2014. MAVEN's mission was to quantify the exact mechanisms and rate of atmospheric loss. MAVEN found that solar wind strips the atmosphere at a rate of 100 grams of gas per second. High-energy protons and electrons bombard the atmosphere at 1,000,000 miles an hour, smashing into molecules and ejecting them into space. This process of collision and acceleration is known as Jeans escape. As particles collide in a cascading barrage of energy, atoms with low molecular mass, such as hydrogen, will reach escape velocity much easier than heavier nuclei. If an atom is able to travel a free path far enough, Mars's low mass will be unable to pull the escaping atom back into orbit. This stripping process can help to explain a loss of water during the Middle Hesperian period and the current fate of water vapor in the atmosphere. At low temperatures and pressures, water evaporates or sublimates into water vapor. The vapor in the lower atmosphere will undergo a series of photochemical reactions forming hydrogen and oxygen gas. The lighter hydrogen and oxygen produced from these processes escapes the atmosphere easier than its original heavier vapor form. Although in small quantities, we have observed pockets of ice mixed in with frozen CO2 at the poles that when exposed to low pressures will be free to start these physical and chemical reactions. Methane continues to be a hot topic even off-planet. In the early 2000s, small variable amounts of methane were found in the atmosphere with unknown origins. Methane can be a biosignature of respirating microbial life, so astrobiologists fostered reserve hope at its discovery. Unfortunately, the measured methane likely resulted from a number of non-biological processes, such as radiolysis of water, producing hydrogen gas, which can then combine with carbon in the atmosphere to form methane and other hydrocarbons. If we were to see methane from biological processes such as methanogenesis, ethane would likely be measured as a byproduct of this respiration. Understanding the Martian atmosphere is critical for understanding the habitability of the planet, either for microorganic extremophiles or future human colonies. An atmosphere provides the pressures and temperatures for liquid to exist on the surface, which is a necessary component of all life as we know it. As you all may know, free-flowing brine solutions have been discovered on hillsides which could potentially support life. These brines are thought to be mostly chlorate and perchlorate solutions at concentrations that microbes can indeed proliferate in. As water likely existed in the past, Mars may harbor extremely adapted remnant life from a unicellular age similar to early Earth. But the extent of microbial life can only proliferate so far without protection from the atmosphere. Understanding the rate of solar stripping on Mars provides us with knowledge of how a low-mass planet without a magnetosphere is affected, if these processes can be changed, and the potential future of our own planet. Utilizing an accessible experimental planet should be of the utmost importance for exoplanet research. Humans have always had a fascination of Mars, and it will continue to intrigue humanity both scientifically and romantically for centuries to come. Today, we are feeling the same pull towards Mars as we once had towards the Moon. After the first rover landed on Mars in 1976, Ray Bradbury expressed his thoughts on the historic achievement. Today, we have touched Mars. There is life on Mars, and it is us. Extensions of our eyes in all directions, extensions of our mind, extensions of our heart and soul have touched Mars today. That is the message to look for here. We are on Mars. We are the Martians.